What exactly is light? Throughout the 18th century, most scientists preferred to model the behavior of light with a particle. Sir Isaac Newton made the model popular, and for years his personal fame protected it from attack. But by the early 19th century, the particle model had been eroded and replaced by the wave model of light behavior, which was first proposed many years previously by Christian Huygens. The wave model explained many behaviors of light, but it was far from perfect. For example, no one had been able to prove the existence of the mysterious invisible ether, the medium which filled the air and space around us and was apparently necessary to convey light waves. In the mid-19th century, a remarkable scientific mind added a new twist to the wave model. James Maxwell was a theoretical physicist. He worked principally with mathematics. Maxwell made a brilliantly conceived prediction. Light is a wave, formed by two of the fundamental forces of nature, electricity and magnetism. Just what knowledge did Maxwell have to work with? It was known that when electricity flows through a wire, it creates a magnetic field around the wire. When the rate of flow changes, the strength of the magnetic field changes too. Maxwell was also aware of a closely related phenomenon. If a magnetic field changes in strength, an electric field is produced. This will cause a charge to flow through the conductor. Could a single particle carrying an electric charge have similar fields associated with it? Maxwell theorized that when a single charged particle moves, it creates a magnetic field. If it changes speed, the strength of the magnetic field will also change. Could this changing magnetic field in turn induce a changing electric field, in turn producing a change in the magnetic field, and on and on? Maxwell constructed a mathematical model to make one of the most important predictions in the history of physics. His calculations predicted that if a particle which generates an electric field is accelerating or oscillating, it creates a changing electric field, which propagates away from the charge its strength changing in the form of a wave. At right angles to this changing electric field is a changing magnetic field, also propagating as a wave. These fields need no medium, such as ether, to convey them. Just as a magnet, for example, works in any medium. And just as the electrical force between two charged particles acts, even in a vacuum. Maxwell's calculations showed that these electromagnetic waves can reinforce each other endlessly, but only if they propagate at one particular speed, a little more than 300,000 kilometers per second. And that just happens to be the speed scientists had calculated for light. Is light a form of electromagnetic radiation? A fascinating possibility. But there was no evidence that electromagnetic waves really existed until another giant of physics tackled the problem. Heinrich Hertz set out deliberately to find physical evidence of Maxwell's electromagnetic waves. He built an apparatus using a transformer to increase voltage and produce a spark between two terminals. This spark caused a charge to oscillate backwards and forwards between two plates attached to the terminals. Is this device a transmitter of electromagnetic waves? If so, how to detect the waves? Hertz tried many devices, including a single wire loop with a small gap in it. Hertz placed this antenna near his transmitter and was able to observe tiny sparks jumping the gap in the antenna. Clear evidence that the loop had absorbed some of the energy emitted by the transmitter. This work confirmed Maxwell's prediction that electromagnetic waves result from accelerated charges. Scientists have since discovered an infinite range of different electromagnetic waves. Because they all travel at the constant speed of light, they can be identified either by the length of a single complete wave or by the number of waves that pass a point in a second, expressed as cycles per second or Hertz. The wavelengths which Hertz used in his experiments are today called radio waves. On a scale of wavelength, radio waves range from many kilometers in length down to a few centimeters. Shorter than radio waves are microwaves, ranging down to wavelengths of a few millimeters. Still shorter are the infrared waves. We feel these as radiant heat. The electromagnetic radiation we actually see, visible light, is an extremely narrow band of wavelengths, only 2 × 10⁻⁷ meters wide. Shorter than visible light waves are ultraviolet rays. Shorter still, X-rays. And on down into an endless sea of incredibly short gamma and cosmic radiation. Over the last century, we've discovered or created transmitters to produce a vast range of this radiation. Light itself is transmitted from accelerated charges within atoms. Maxwell's electromagnetic wave model was so useful that for nearly a century it seemed the final explanation for the behavior of light.